All right, kiddos. So the best model that we've got so far is the Bohr model, right? And remember, the Bohr model said an electron must be in a stationary state, right? Because if it was orbiting, you would have an atom constantly emitting light, right? Electromagnetic waves. But it must be stationary, right? This must be true because stable atoms don't constantly emit electromagnetic waves. Okay, so it's not constantly emitting light. All right, but from our lesson last class, an electron can act like a wave. And so Bohr theorized that an electron in his model would act like a wave. Right? And remember, the de Broglie wavelength for an electron has to do with Planck's constant and the momentum of that electron. Okay. Now, if an electron is not moving in an orbit, right, but it's existing in a circular energy state. And so Bohr then theorized that electrons have an angular momentum. Okay. And we haven't learned about angular momentum as part of our course, as part of the engineering physics option, but I'm just going to kind of talk you through angular momentum. So it's mass times velocity times the radius of the circle, where mv is obviously linear momentum. And he said it was related to n, okay, which energy state, right, which circle in the Bohr model the electron was existing in, right? So the ground state would be n equals 1, the first excited state would be n equals 2, the second excited state would be n equals 3, or the third energy level. So that's what n is, Planck's constant, and then because they're existing in circular energy states, it's in over 2 pi. Okay. So what we can then do is take this equation and solve it for momentum. Okay. And stick this in right here for momentum. Okay, because mv is linear momentum. And so we get h over wavelength is times r equals nh over 2 pi. Okay, and these are both h's. Those cancel out. And if we rearrange this, we can get the wavelength of an electron existing in a certain energy state is equal to 2 pi times r, the distance from that energy state to the center of the nucleus, over which energy state it's in. Again, ground state is 1, the first excited state is 2, so on and so forth. Okay, so that is what Bohr theorized. And so he was saying it was an electron is acting like a wave that has a certain wavelength that changes depending on the energy state it's in. And so instead of it orbiting, right, it's acting like a wave, and we can predict the likelihood of an electron to be in an energy state using Schrodinger's equations, right, like we talked about last class. Okay, and for a hydrogen atom, which is really all that we're going to talk about because it's easy to conceptualize at this level, Schrodinger's equation simplifies for a hydrogen atom. So Schrodinger said, okay, let's include the out there. He says that the energy that an electron has in a hydrogen atom is equal to a constant. This is a capital C. There's a negative sign there. over n squared. Again, where n represents which energy state an electron is in. Now this capital C, again, is a constant. It's a pretty goofy constant. It's equal to 2 pi squared times the mass of the electron times the number e to the 4th power times Coulomb's constant squared over Planck's constant squared. Two things. Whew! And what? Okay, so I'm not going to go through where that constant comes from because it's not necessary here. But you know what is pretty nice is when you do all of that math, you'll get that the value of C is equal to 13.6 electron volts. And that's a number that we can deal with. So for specifically a hydrogen atom, we can find how much energy an electron has by taking 13.6 electron volts and dividing it by its energy state squared, right? So if we do that for n equals 1, if we put 1 in here, we would get an energy that the electron has in the first energy level is negative 13.6 electron volts, right? If we put in 2, if the electron is in the second energy level, also known as the first excited state, we would get that that electron has negative 3.4 electron volts. Now, why the negative? Okay, that really is how deep the electron is in the potential well. So if you guys think about with the photoelectric effect lab, this represents how much energy it will take to get an electron from this energy level, right, up and out, ready to be liberated from the hydrogen atom. Okay, it brings it up to the surface. You can also think of it as the ionization energy of an electron that's existing in that energy state. Okay, so it's negative because that's how much energy is required to get the electron unbound to the nucleus of the atom. Okay, and then how much energy is required for an electron to go from that first energy level to the second energy level? Well, the energy required for an electron to make that jump is just the difference in the energies here, right? So what's the difference in 13.6 electron volts and 3.4 electron volts? Well, it's 10.1 electron volts. So that's how much energy is required to get that electron up to the second energy state. No more energy and no less energy. Okay? And so what we're going to do is I want you to actually take some time and do a little bit of investigation with this. There is a simulation. It's actually intended as an astronomy simulation. And it is, whoops, let me find this for you guys, just a moment. All right, here is that simulation. There's a link on the Google Classroom for you, but I just wanted to kind of give you a tour of what it looks like. Okay, there'll be a handout that I'd like you to use to kind of focus your investigation and record your findings to make sense of what you're seeing. And then this simulation, what you can do is this is a hydrogen atom, right? Here's your little 1 proton, that's the nucleus of your hydrogen atom. And here's your little green electron. And these are all of the other energy levels, okay? You can see those energy levels here on the right-hand side, kind of drawn like I had on the slides previously, where there's energy level 1, 2, 3, 4. Okay, and what you're going to do is you're going to shoot photons at the atom. Remember, photons can give electrons energy when they collide with the electrons. And the amount of energy that the electron gains is the energy of the photon, where E equals hf, right? So you can change the frequency of the photon. You can change, in turn, the wavelength of the photon and how much energy that photon has. And you can do it manually, like this, with the slider, and you can just fire a random photon, whoop, and see if it does anything to the electron. You can see that one, it says this 5.3 electron volt photon was not absorbed by the electron. Okay. And then you can keep doing this manually, but something else you can do is there are specific frequencies that do cause energy level transitions in specific instances. So P beta, that was a 9.7 electron volt photon. It was not absorbed. So that P1 didn't work. What about H gamma? 3.02 electron volts. What did we just calculate was the amount of energy that we needed to take that hydrogen, the electron in the hydrogen atom from the first excited state to the second? It was 10.1 electron volts. So these are all smaller electron volts. Let's go up here, maybe L alpha. Ooh. See what happens? Oh, it's 10.2 electron volts. Maybe I mathed wrong. Yeah, so it says down here that that photon came in and took your electron from the first energy level to the second energy level, and those 10.2 electron volts were absorbed. And then it shows the electron was de-excited. It popped back from the second energy level down to the first, and it emitted a photon that had that 10.2 electron volt energy. Okay, so play around with all of these buttons. See if you notice any patterns, right? Record any observations that you have, and again, use that student handout for guidance. If you need some for exploring this simulation, it'll focus your work. All right, kiddos. Okay, take a look at that. At least play around with the simulation for a little bit, and then when you come to the class time next week, we'll debrief what you found and answer any questions. But I would like everyone to take a look at this simulation just a little bit to be ready. Okay, you guys, I'll see you next week. Stay safe and let me know if you guys have any clarifying questions. Bye-bye.